Start the recording and say hello. How is homework 4 going, folks? That well, huh? Don't all talk at once. I have it open if anyone wants to ask specific questions. It is due Monday night, so hopefully getting started soon if you haven't already. I did post the Word document that I built during class to talk about interaction terms and simple slopes right here. So that may help you figure some of those out if you're struggling. Another thing that I saw in terms of errors folks are making in terms of generating the predicted outcomes. So the very last numeric questions are enter the predicted count of foods given whatever levels of your predictors. You need to enter a value for all predictors in the model. Otherwise, it will fill in, I think, the mean of the predictor. So for instance, the first one is asking the predicted count of foods given no younger or no older siblings. You have to fill in 0 for those two predictors. Otherwise, it will do whatever is happening on average. Likewise, 0 food school sessions involves both predictors being 0, not just the binary version of it. So. And then predicted count means that you're trying to get these predictions within the data scale, not the model scale. So making sure you have the right options for that will also be useful. So, no homework questions? All right, well, you can send me emails, excuse me, not the TAs. I don't expect them to work over the weekend. I'll answer your questions over email, and I'll be in office hours Monday. So we'll make it work, right? Oh, that was a lack of enthusiasm. Make it work. Maybe I can cheer you up by showing you what little we have left for the semester. We are winding down. So I finished grading your homework 5 plan templates. And for about half of you, I had extra questions relative to your data or what you were planning. And so I gave you 1 point with instructions that said, please answer my questions and send it back. So your feedback is available inside the homework portal. That's where you should find a link to your document with my comments. And I put up a new homework 5 plan revision spot in icons for you to submit those. If you could please get those done by next Wednesday, so about a week or so. That way, that'll give me time to turn them back around and make sure that I know what you're going to be doing. So homework 4 is due Monday. The next week, we have our formative assessment number 5, and then homework 5 is due the 22nd, and I put up the instructions for that this morning, as I think I announced over email. So what you should be doing and what the points are worth are all described in here. If you have questions about what you should do, please let me know, and I'm happy to try and clarify. And revisions to homework 5 will be due at the end of finals week. Homework 6 will be another CAN data assignment. You get to practice path analysis. And to be able to do that, you will have your choice of using Lavon, which is a package in R, or M+, and all of you in this class should have access to M+ using the Iowa Virtual Desktop for free. So please, at some point within the next week or so, check to make sure you can get to M+, and if not, I will need to track down the tech folks and get help. If you haven't used the virtual desktop in a while, make sure you download the most recent version and then restart it, and then M+ should be there. So if you haven't downloaded the new version, you may not have access just yet. But that's going to be it. So any questions about due dates, outstanding work, and that kind of stuff? Okay, well, I'll take the silence as a no. All right, I'm going to change gears a bit. So I had a question over email about sort of generally, can we try to organize what we've learned this semester in terms of like an action plan, like if this, then I should do this kinds of things? So I thought that might be a useful thing for us to do. I'm building an Excel spreadsheet in which to do this, and I will post this after class so you can listen along or type along as you see fit. So in this class, we're focused on generalized models. I'll start with that, but I also want to include the standard type of regression as a point of comparison. So do you remember what the first type of outcome is we covered? in terms of generalized? The one that's the easiest? Where did we start? Unit 2, homework 2. 2 months ago, give or take. What was it? Binary, yeah. So if I'm predicting a binary outcome, I need some kind of generalized model to do that. What kind of link function would be appropriate for a binary outcome? Logit's one. Give me another. Probit. Probit. And if you're in the IRT class, what is that called? Ogive, yes. And why these link functions in particular? What makes them designed for binary data? Two boundaries, yes. So in binary data, what we're trying to predict is the probability of having a 1 or a 0. And probability is bounded below at 0 and above at 1. So we need some kind of link function that reels in the predictions in between those two. I'm going to leave just those two for right now. What kind of distribution would we be using for binary outcomes? Also starts with a B. Somebody's name, I think. Yeah, Bernoulli. I think that's how you spell it. Close enough. And if you are writing a results section in which you are trying to describe to your reader that this is your setup, what do you call it? What have you done? What would normal people call your model? Logistic regression. That's what they would call it. That's correct. Logistic, or, because that would be if you used a logit. It's probit regression. It's not probistic, even though it seems like it should be. It's just probit. Okay, back this down a little bit. All right. Now, I've added a column here. What might I need to worry about? In this case, do I need to worry about how well the distribution fits? No. What about links? There's one thing that I would be concerned about, and I'm going to put this down. Asymmetric. That's not quite right. 2 M's? Close? Yeah, it's like I can't spell it to save my life, but if you have a binary outcome that has way more zeros or way more ones, there are asymmetric link functions that might be more useful, and these are C log log or log log. C stands for complementary, and no, I will never remember which is which. I get out my own slide whenever I have to answer this question. I don't remember. If you are in that situation where you have extreme skewness, these are alternative link functions that weight the prediction that on the side that has more information. So like it looks like a logit if you have a whole lot of ones, but it sort of peters out on the other side because you don't have that many zeros, and it's not going to be able to predict it. To do this, we could compare models. Let's see. I'm going to add another one out here. Another cell to my table. On this one, we would compare AIC and BIC. So these are known as information criteria. They are transformations of -2 log likelihood. So given the same distribution, we can compare the fit of alternative link functions and decide which one is relatively preferred. And for AIC and BIC, do we want them to be big or little? Little. Little, always. Doesn't matter what software you're in, little is better. Okay. What do we do next? Ordinal. What kind of link function do I need for ordinal? Give you a hint. Has this part as an ingredient. It's logit, but it has one more word in front of it, or probit. Here's what I'm contrasting against. The next one is going to be nominal. What distribution do these two use? Starts with an M. Not someone's name. We'll play hangman. Yeah, I heard it. Oh, not multi-level. Wrong class. Yeah, this is the first semester I haven't said anything about multi-level in a very long time. I kind of miss it. It's my jam. What is it? Multivariate. That is our next unit, but not the end of the word. I know there's a lot of M words that start with multi, isn't it? Multi, N. Oh, I heard it. Multinomial, yeah. So it's basically, this is for 2 categories, this is for 3 or more. And it's for both of these. Okay. So the difference between ordinal and nominal lies in the link function, not the distribution. For ordinal, there's a word that comes before logit or probit. It starts with a C. It's based on the idea that the submodels that we build to predict an ordinal outcome use all of the categories. So like 0 versus 1, 2, 3, 4, 0, 1 versus 2, 3, 4, 0, 1, 2 versus 3, 4, 0, 1, 2, 3 versus 4. Cumulative, yes. Cumulative, logit or probit. What about for nominal? Does that type of link function make any kind of sense? Probably not. They're not numbers. They're not ordered. So there's another kind, and this has a couple different words to it. It is known as generalized, which is a word that means about 17 different things, so that's not a helpful one, or baseline category, baseline logit or probit. This is the one that's like dummy coding. You pick one of your reference, one of your answer categories as the reference, and then the submodels give you the probability of answering something else or the reference, something else or the reference. This one is also called, all right, let me get to that next. What is this one sometimes called? There's 2 names that you'll see this as. I would just call it nominal regression. Someone else would call it, what's it called in Stata? No Stata people here today. Okay, we're going to play hangman again. M-U-L-T. Say it again. Multinomial. Yeah, that's what people would call this. It's not a good name because that's the name of the distribution, not the link. And the link is what makes it nominal and not ordinal. But these would be nominal or multinomial regression. How about this one? I would call it ordinal regression, or foreshadowing something in the worry about column. I would have written this in your feedback for your planned homework 5 for those of you who are predicting ordinal outcomes. Tell me about the slopes in an ordinal regression model. In the standard version, did they differ across the submodels, or are they all forced to be the same?
They're the same.
They're the same. That has a name. What is it? Thresholds are related to that because they're the things that get to be different. Those are like the intercept or the threshold gets to differ across the submodels. The slopes are all the same. And so the slopes being the same has a special name. Starts with a P. R, O. P. Oh,
Proportional odds.
hey, proportional odds. But I can't type. Por, no. Yes. I do have a PhD, in case you're wondering, and I still can't spell, especially not in front of people. So in the worry about column then, I'm going to shrink this one. What am I worried about potentially with a proportional odds model? Let me shorten that. Do I have to have a proportional odds model? No? Could I check it? Could I see if the slopes want to be different? Sure I can. So I'm going to put non-proportional odds, something you can check about. However, your power to do that is going to be based on how many people you have in your categories. So for those of you who have ordinal data with not very many cases, this may be difficult. And if I wanted to test whether a model that had different slopes across submodels fit better or predicted better, how might I do that? I could use AIC and BIC, but I might want a significance test instead. Odds ratio is effect size. Yeah, we're going to add another column to that. Yeah, -2 log likelihood. More general name for that? Comparisons of -2 log likelihood? What's it called? I'll give you the acronym. LR? Yeah, likelihood ratio test. So what it is if you have the likelihoods out of the model, then it is the one that has from the model with fewer parameters divided by the one with more. If you work with log likelihoods, then division turns into subtraction, and it becomes -2 log likelihood difference. So it's a confusing term, but the difference in -2 log likelihood as a way of judging model improvement is a universal concept you will see in many, many different contexts. What about nominal? Do I need to worry about anything with this? I'm going to write in here blowing up, because nominal has a separate slope for every submodel. So that's a lot of parameters, and you need a lot of people to be able to pull all of that off. Now I'm going to add an effect size column out here. If I want to do effect sizes for binary data, what should I use? Say it again. You said it 3 minutes ago. Hey, odds ratio. What if I want to do effect sizes for ordinal? Don't think too hard. Odds ratio. What if I want to do it for nominal? Odds ratio, yeah. Odds ratio for the win. Okay, then what do we do? What's homework 4 about? Counts? What did you say? Counts? What kind of link do we need for counts? Logits and probits still, or something different? Just, yeah, natural log. And why only log and not logit? Yeah, the log handles the bottom boundary. The top is unbounded. Distribution. How about this? There's like 4 or 5 choices, maybe 6 choices. See, I'm going to go over here and then I'm going to write distribution fit as what we need to worry about. So this is where the link is pretty well set, but I want to evaluate Poisson versus negative binomial, potentially 0 inflated versions of those. What would we call this model? I would say it's either a count or Poisson. Actually, let me say this more generally. count regression or whatever distribution you're using. Like you will see people say, I did a negative binomial regression. I did a Poisson regression. Like it's called NB-reg in Stata, for instance. What do we do to look at distribution fit? Something new that isn't on the spreadsheet yet. X2, I heard that? Close. Something needs to be 1. What's the something? Some dude? Yeah, Pearson chi-square, the same Pearson who invented like 17 other things. Pearson chi-square divided by degrees of freedom. So that is describing the variability of your residuals in the data relative to what the model says it should be. So if they match, that should be 1. So I'm going to write down chi-square over df for that one, as well as nested model comparisons using likelihood ratio tests. And if I want to do an effect size, incident rate ratios. And you know how you compute them? The same damn way as an odds ratio. E to the slope. There. Okay, what did we start talking about last week and Tuesday?
Proportions.
Yeah, proportions. What kind of link do I need for a proportion? Logit or probit, again, I would say. Logit's much more common. How about distribution? Do I know that, or is that a series of question marks?
It's also question marks.
Yeah. And I would say this would be called binomial regression, potentially. But I'm going to say we need to worry about distribution fit. And this is where we have binomial, beta binomial, 0 inflated or 1 inflated versions of those things. So the same process and logic. And then I'm going to put odds ratio down here again because it's tied to logits. How about something that is skewed continuous, like money, response time?
Identity.
Identity, or what if I want to make sure that my response time doesn't go negative or my money doesn't go negative? Oh, yeah, we got the technology. We can do that. How about distribution? There's really only 2 that I know of that are used for this. One is gamma, and the other is log normal. And they're from different families, so they can't be compared. For name, I'm going, I've seen it called a gamma regression, in the same way that naming things after distributions. I would say in terms of worrying about 0 values, because these are distributions that are strictly positive, so if you have zeros, you need to add a submodel to predict that. And effect sizes can be the incident rate ratios, or they could be R-square kinds of things, because at the point where we have continuous data, we could actually correlate the predicted and actual outcomes. Now, what am I missing from this list? What did you know how to do before you got here? Continuous, yeah, right? So continuous, I would say, and symmetric right? That's the idea of normal, is that something doesn't have boundaries. What kind of link function did you use to predict these sorts of outcomes? You're like, I didn't. Yeah. It's called identity. Not natural log. Yeah, there is no link function. What distribution are we saying it follows? Normal. Yeah. And what would I call it?
Regression.
Yeah. Regression. Or if I had categorical predictors, I might use a different word.
ANOVA.
Yeah. And more generally, I would call that a general linear model. What do I need to worry about? I would say predictions going out of bounds. I would also say heterogeneity of variance. That's not going to fit. How about HV for short? And in terms of things we would do, we don't typically do anything to compare alternative models. If it's not normal, it becomes part of something else. And effect sizes, we could say R-square type things in that column as well. So these are all what I would refer to as univariate analyses, meaning we're predicting one outcome at a time, assuming that people are independent. So what if that's not the case? What if, let's go with those three. Crossover event. What are these three models called if you're predicting multiple item responses at the same time from a latent factor instead of an observed variable? Crossover event. Predicting categorical outcomes from a latent variable. Multiple items at the same time. Yeah. What's it called? Yeah, it's within the factor analysis family. Yep. Yeah. So I'm gonna insert a column over here for the crossover. Cross. IRT. That's what this is called, but it's the exact same set of concepts. I would call these ones IRFA or IRT to be complete. Item factor analysis. Those. This one doesn't have a name in the generalized SEM world. Neither of those do. But this one does. What if I'm pretending that my data are continuous and a latent factor is my predictor?
CFA.
Yes, confirmatory factor analysis. Same technology, same ideas. Okay. Not just crossover, but foreshadowing. What if you want to predict a binary outcome at multiple occasions? Can I do that? Can I do that using just this? Nope. So where these models have to grow for dependent data is to be able to say, hey, can you let the outcomes from the same person be related beyond just the predictors? And that happens using what is known as random effects, which you can learn about in coursework on multi-level modeling and longitudinal analysis. So we'd have to add some more columns of options for addressing dependency and how we build a correlation into the model. But guess what? We're going to do that next week. We're going to start on that. because I want you to understand modern approaches to multivariate analysis via path modeling. Because you can do that for general or generalized outcomes, and you can do that for repeated measures from the same person, multiple items, multiple occasions, and so forth. Okay, so there's my taxonomy of, at least for this class, where we've been. But these are the building blocks, the Lego pieces, if you will, to being able to predict these types of outcomes in more complex samples. All right, how'd we do, Dan? This better? Okay. Any questions or things that I'm forgetting out of this?
Should there be anything in the compare cell with the rows that are empty or can we put question marks there / NA? So we know it's blank?
I would go with NA, because if you have a nominal model, there's not a question about which distribution, and the default in nominal models is that each submodel gets a different slope already. So you could potentially seek to simplify if you wanted to, but I don't think that would make sense in most contexts, because you're predicting like literally different things. So I'm going to put an NA there. In terms of comparison, yeah, not really much to do with distributions on these either. And they're from different families, so you can't use AIC or BIC. And for comparisons involving regression, those would not be of the same kind. They would typically be focused on which predictors you need, but that would be true for any of these models. So nothing special about the generalized part with respect to that. Question?
Yes. When it comes to effect sizes, there are more options than these for some of these, right? Like,
So for like these kind, there are other kinds of ratios that people will build, like a relative risk ratio instead of an odds ratio. That has to do with what your denominator is. Some of them work better for more infrequent events. In terms of things that are into numbers, I would say that once you get into something that behaves like a number, you can do R-square type of things. You can compute like a predicted proportion and correlate it with the real one and build R-square kinds of things. Within the world of normal, R-squared is one thing, but then you also have things like semi-partial or partial R's, which are R-squares with different denominators rather than in terms of total versus unique. You can also compute things into D's and whatnot, but that is true for any of these. It's just that the odds ratio family is much more prevalent as a measure of effect size. Yep. All right. Then I'll leave that here. I wanted to talk about something else to add to your toolkit, quantile regression, as foreshadowed last time. Slide 17. So in continuous data, we might be concerned about outliers that are dragging our prediction awry. Basically, the idea that people worry about with outliers is that they could drag the regression line more than other cases, like they have undue influence on the solution. I don't like the idea of data cleaning and outlier removal because it's very subjective as to what's an outlier and what's not. And if they are real values, then it seems unfair to kick them out. So if you have someone who's lying to you, right? Like if you ask, how many hours a day do you play video games? And they say, I play video games 25 hours a day. Like, maybe you don't want to use their data because they're not taking it seriously. But if someone said, I play video games 20 hours a day, I'd say, you should really meet my kid because he has the same level of dedication. So that may be a valid value. And who am I to say that they shouldn't be part of my analysis? Like if I want to generalize to people who have extreme behaviors, then I should have them in there. So a solution to this problem is to change the regression model into predicting a different expectation. So normally in standard general linear models, we predict the conditional mean, which gets notated with this y hat thing. And the way that the model, let me put it this way, the way the estimator decides what the best fit slopes would be is that though they minimize the sum of squared residuals. So there's a more general term for this called objective function, meaning what is the thing that you're trying to minimize or maximize to be able to decide what is relatively best. And the formula looks like this. So basically it's the sum of the squared e's and over people, and minimizing that is the point of the show. And there's a very easy closed form solution. In matrices, it's x transpose x, so inverse x transpose y. I don't make you learn matrices, but point being, there is an answer, right? Like, people don't have to do this iteratively. It just falls out. You can do it on your calculator if push came to shove. So this is very convenient to be able to maximize the mean, in part because this function has a curvilinear part to it, like where the minimum is. It makes it easy to differentiate. However, if you have a lot of skewness and or outliers, we can use the median instead of the mean. And the process works similarly after we change what the objective function is. So this is the idea of quantile regression, where you can predict the conditional median as opposed to the mean, or any other percentile. And what it does for its objective function is minimize the absolute value of the residuals instead. So this does not have an easy closed form solution because the function is pointed, and you can't differentiate very well once you get down to this point. So in order to do this, we can figure out what the slopes are, but we can't easily figure out what their standard errors are. So people have worked around this by doing resampling types of things to get the standard errors, one of which is bootstrapping. So that should be a term that you've at least heard before. The idea of resampling so that you can characterize your sampling distribution using just the one sample, resampling with replacement. Another thing you might see is jackknifing, which is everybody minus one. So these are options that you would need to specify in the software how many samples you want to do. And that also means that you need to specify what is known as a random seed to be able to get the exact right answers back in terms of replicating what the bootstrapping algorithm is doing. Otherwise, every time you run it, you'll get a slightly different result. And so in my syntax illustrating this, to avoid that problem and make sure that no matter when I run my example, I get the same answers, I use the random seed as Jenny. And some of you may not know what this means, but there's an 80s song, and the title of the song is Jenny, but it's her phone number is what they sing in the song. And it goes 8675309, 8675309, and it's a whole thing. So based on that, my random seed forever is going to be Jenny, because that's a number that I can remember. Last time I taught this class, I had a student in here who not only had a wife named Jenny, but she had a t-shirt that said 8675309. Like, she bought in, so. I know, I would love that too. But if you see this number, this is why. This is my random seed. So here's the software that I found that will be able to do this. So we're still assuming independent residuals with constant variance, but we're not necessarily assuming normality because we are not using the normal distribution to get standard errors. We're using this alternative way of doing it. So if we can predict the 50th percentile, we can predict any percentile. And where I see this being useful is to essentially find a way to specify predictor by outcome interactions. So here's some examples that I thought of that would illustrate this. So if I'm doing a student intervention, is that more effective relative to some control condition in helping low-performing students or high-performing students? So I could try to predict, for instance, the 25th percentile and see what the intervention effect is at that point on the distribution. And I could see to what extent I have an intervention effect at the high side, say 75th percentile, and I can do a significance test to see whether there's more, whether the slope works more at one point versus the other. An example that I had done previously, but not in this class, is looking at cognitive aging and measuring response time in older adults. Answering the question, does age predict response time to a greater extent amongst the slower responders than amongst the faster responders? And the example that I did build for you is about house prices. So we know what makes a house valuable. Usually it has a relation to its location and its size, but we might ask, does having more square footage matter more if you're in the sale of cheap houses than if you're at an expensive house. Like, you get more bang for your buck by adding on to your basement or adding a bathroom if you have a smaller house than a larger house. Unfortunately, I have found very few applications that extend this model to dependent samples. Like, multi-level quantile regression is not a standard thing. There's no reason it couldn't be, but it's not a thing you can find easily. And very last slide here, in the case of ambiguity. So if you are looking at your taxonomy, right, and this is nice and clear, but the real world doesn't work this way, right? You may have outcomes that are not normal, but they're not categorical and they're not counted. You're not really sure what to do with them. There's one more set of options that you have at your disposal, which is to ask for robust standard errors. Most software packages have an option to do this. And what it's trying to do then is to use the actual distribution of your outcome to try to figure out what the standard errors should be. So it's a data-driven kind of approach. Here are the options by which you can find this within Stata, within SAS, and then within R, of course, it's package specific. There's one other thing that you will see in relation to this: cluster corrected standard errors to address dependency. And even though this is a thing that is commonly available and commonly done, I would caution you not to do it. If you have people that are clustered into naturally occurring groups, such as students nested in schools, or you have workers nested in companies, then every slope that you're thinking of as a person characteristic is also an organizational characteristic too. And each of those slopes would need to have different effects in your model to prevent misspecification, and the cluster correction on that has no effect on that whatsoever. So you can end up with accurate standard errors to inaccurate slopes. So I include that as a cautionary tale for that purpose. If you want to figure out how to model cluster data correctly, come to the multi-level modeling classes. It's a good time, right? Several of you have been through that. It's a good time? You're like, no, it's not a good time. I don't like it.
I need a baby blanket during it.
You what?
I need a baby blanket during it.
You made a baby blanket during it. See, that's productivity. That's nice. I like it. But let's see some quantile regression. Why not, right? And in so doing, I want to make sure you all know how to interpret a quadratic regression coefficient. That's my other secret purpose of this example. Because if you come to longitudinal in the fall, I need you to understand what to do with the quadratic regression coefficient, because that's used very commonly in modeling nonlinear change over time in longitudinal data. So this example is ostensibly real data, but I have my doubts. This came from chapter 4 of the Agresti book, whose chapters are on your reading list. These are sale prices of 100 homes, and I am coding 4 different characteristics as predictors: whether the house is brand new construction, square footage in the hundreds centered at 1,500 square feet as a reference house, the number of bedrooms, 2, 3, or more than 4, 4 or more, number of bathrooms, and the distribution, of course, is bounded by 0 and is positively skewed for house prices. So we're going to look at different options for fitting that. And I have the usual disclaimers about what it took to get things to agree across packages. So I am doing a coding scheme here that is a little bit atypical. I am making the reference for these categorical predictors the middle one. So I have 3 bedrooms as my reference, and I want to know what happens if I only have 2 or if I have 4 or more. Same thing with 2 bathrooms as my reference. I want to know what happens if I only have 1 or 3 or more. So my reference house has 3 bedrooms, 2 bathrooms, and 1,500 square foot, and is not new construction. So the coding that I did accomplishes that. So I have, in terms of my labels of things, bed 3v2 means 3 is the reference and 2 is the alternative. And 3v4 means 3 is the reference and 4 is the alternative. So this is an ordinal measure, essentially number of bedrooms, but I am making it so that I can get adjacent differences between the two. Same thing with the bathrooms. Rescaling square feet, and then I'm also making a squared version, because I think that having a bigger house only helps up to a point, and then more doesn't help. So I'm operationalizing that idea with a quadratic function. Here are the packages I'm using in R to do this, and the same data transformations for creating predictors in pictures. So here's my picture. This is the distribution of house prices in this data set. So you tell me, where does the outlier start? These two? Do they look like outliers? Kinda. They're sort of far away. These are houses that are like $580,000 or something. How about this one? Is that an outlier? What about that one? And this is the problem. Is not a useful thing to write in a results section. What's your question?
Oh, it's like writing the result section. I have a question about this data point.
Yeah. But could a house cost $580,000? Yes, it could. Could a house cost $20,000? A tiny home, maybe? I don't know. A tiny, tiny home? A shed in your backyard, especially in California or something? So here is a plot trying to look at the distribution and where the various reference points would be. So if I used interquartile range, for instance, all of these houses would get dropped. But these are real houses with real prices, so that makes me uncomfortable. So we're not going to do that. We're going to explore some alternatives. So I'm using the same linear predictor throughout all the models and just fitting different types of models. So here's my equation. Whether or not it's new, number of bedrooms, number of bathrooms, and then square footage. This one, the main effect, is going to be called the linear slope for square footage. And beta 7, that is attached to square footage squared, is the quadratic. So we're changing notation in terms of how we talk about it a little bit. Each of these is a linear slope, and I don't need to say linear because there is no other alternative. Whereas these are both effects of square footage. So first option, can I just pretend that this is normal? Let's see what conclusion we come to if I do that. So I'm using maximum likelihood estimation to keep it comparable with the others. And here's some outputs. Do I have, nope, I don't have it. Okay, well let's look at it. Let's look at the R output. This is just a standard general linear model. Gaussian link equals identity. By the way, to do a squared predictor, this is how you would do it in R. It got mad at me in some of my Lincom type things, and so I just wrote it out as the squared version myself. And I don't know why new is blue. It's new! I don't know. There we go. That's better. Okay. Practice time. Intercept. What kind of house is this for? Costs $128,000. Not new. It's an existing house with how many bedrooms?
3,
How many bathrooms?
2,
And how big is it? Yeah, so I divided it by 100 so that otherwise it would be per foot and that slope would be teeny, teeny, teeny. So this is 1,500 square feet is the reference. So what happens if your house is new? Does it cost more or less? More, you would think. What happens if you only have 2 bedrooms instead of 3? Yeah, it costs more, non-significantly. Actually, this is the p-value, but it costs more. Now that might seem strange, but I can point out 2 things that makes it less strange. Number 1 is, do you think that there's a correlation between square footage and number of bedrooms and bathrooms? Bigger houses have room for more stuff. So keep in mind that these are the unique effects after controlling for the other predictors. So what is it about a 2-bedroom house that is beyond how large it is, for instance, versus a 3? And I believe that these are expensive condos. That's my guess. Like apartments that you can like buy downtown, they're not going to have 3 bedrooms. They're going to have fewer, but they have other things that make them more expensive, like pools and doormen and stuff like that. If you have 4 bedrooms, Non-significantly higher. What if you only have one bathroom? Yeah, lower. Non-significantly, but no, I'm going to call bullshit on that one. If you only have one bathroom, that is a problem. I grew up in a house with one bathroom. Yeah, it's I don't want to do that to anyone else. But 3 bathrooms makes it cheaper. Yeah. But non-significant. So we got nothing except new construction right now. All right. How about how big it is? Does that matter? Okay. So here's your tutorial on what to do with quadratics. How do I talk about this number right here? Is that the slope of house size, the end of the sentence? Or is there more to it than that? More to it, right? Now, what do I have to tack on to the end of the sentence to make it correct? You may not have heard this before, but I'm seeing if you have. Does anyone remember physics from high school or college? No? I don't either. But I can tell you that this is analogous to velocity, and the squared term is analogous to acceleration. If that helps. I can do it a different way. This is a main effect. The linear effect of square footage is like a main effect as part of an interaction, and square footage squared is the interaction term. So do you remember the rules about main effects that are part of interactions? Their slope is specifically when the interacting moderator variable is 0. So that is still going to be true for this term. So this is the slope specifically at 1,500 square feet. It is known as the instantaneous slope because it is at the point. It is the line, the slope of the line that is tangent to the curve that is being created by this quadratic model. Now, what does the squared term do to it? Remember the 4 kinds of interactions? Interaction takes it more positive, less positive, more negative, or less negative. Which one is this? More positive. So putting that idea together, does square footage matter more or less in bigger houses? More. Exactly right. Now, how do we deal with the coefficient? There is a very simple rule that you need to memorize. Multiply it by 2. Because of what? So square footage is interacting with itself as the main effect. And to talk about how the interaction, the quadratic effect, moderates the linear effect, we have to multiply it by 2. So what we would say is that per unit square foot, which is 100 feet in this, the effect of square footage becomes more positive by 0.3.
Why do you want to use this interaction term?
It is an interaction term. Mm-hmm. Why do we have to multiply it by 2?
Why do you want to use the interaction term in this case?
In this case, because this thing is going to fall in and out of significance across models, is number 1. Why would I put it in? Is that the question?
Yeah.
Because I don't think that in terms of square footage that more is necessarily better the whole way. Like, I think at some point you have diminishing returns as to how much more your house costs given how big it is. Or it could be the other way, which is what this pattern is that the curve would look, let me get paint out. Why not? Okay. Yeah. So this one is accelerating like that. It's taking a positive slope and speeding it up. Not quite that steep, but maybe something like that. So the linear slope that you get, you have to know exactly where the 0 point is on this predictor. It would be the line that is, the slope of the line tangent to the curve at that point is the linear. The reason why you need to multiply it by 2, one of them is because what we're actually doing is getting the second derivative with respect to the predictor. And when you differentiate, the 2 that was in the exponent comes down in front for the rules of derivatives. The other way that I can explain this is in terms of interactions. So if I have x by z as an interaction term, then the interaction term does two things. It makes x have a different slope as a function of z, and it makes z have a different slope as a function of x. So it operates twice. In this model, I don't have a second main effect. I don't have a z. I only have an x, and x multiplies itself. So whatever it would have done to the other main effect, it has to do twice to x. That's my explanation. So the quadratic coefficient takes the linear slope and makes it more or less positive or negative by twice the quadratic coefficient, and that's the rule. So it looks like house size matters more the further up in house size you go, but not significantly according to this model. This is just a standard model. Nevertheless, if I do a joint hypothesis test of my 7 slopes, it's wildly significant, meaning that I do have a significant prediction of house price from these things, even though only 2 of them are individually significant. Here's my residuals. Is this model good enough? This is not so bad. This one, though, what happened to this house? Like, it's way, way under predicted. So it looks like we have some heterogeneity of variance, potentially. We have houses that might be predicted to have, you know, cost no money, that kind of thing. You can go out of bounds. So, yeah. Well, here's one way to fix it. Log it. This is a data transformation, essentially. So identity link and a log normal condition, no, hang on. Yeah, I log transform this one. So I log transform the data and then fit the same linear model to it. And lo and behold, I get very different answers. So new construction, now marginally significant. Square footage, now I have a declining positive effect. That is significant. So not just the p-values here, folks, like the conclusions are changing as a function of this. This pattern, what would I call this? The quadratic is taking it and making it more positive, more negative, or less negative? Less positive. So this would correspond to, let me get a different color here. Something like this. The idea of diminishing returns. However, a quadratic model is, what would it predict would happen after this point? Does it stay up here forever? No, it comes back down like that. So at some point, having a bigger, having more square footage would make your house cost less. Unlikely, unless it's a condo. Here is the actual log normal model in Procglimics. And Stata, yeah, I don't have the output, but it's exactly the same. Here's an alternative. Here's log link and gamma. So this is for skewed continuous outcomes that don't have zeros. And in Stata's GLM, it actually gives a different result. And so somebody fixed it with a routine called L-gamma that I downloaded. In terms of these, we get yet another set of conclusions. So now new home price is marginally significant, but not significant if I go with a strict 0.05 cutoff. Same thing with my quadratic term. Here is the variance-related scale parameter. that's part of that distribution. So it's letting variance be a function of the mean, multiplicative as well. Here's the, let's see, odds ratio version, IRR, for that. Here's the analog in R. Using the standard GLM package, you can fit a model that has gamma as your distribution with a log link. And here's distribution fit. It seems pretty happy. It's actually under dispersed, so this is a little bit lower than we would like. But it's the only one that I know of that has a measure of distribution fit. The others do not. Okay, then we get to the quantile stuff. Okay, so what if we predict the median instead? Here's what it looks like in ProcQuantReg. Here's what it looks like in Stata, SQReg, where I'm asking for the 50th percentile. And here is what I could find in R, RQ, and this is all I got. Coefficients and then some kind of confidence interval. And I tried looking for how to get other stuff and couldn't figure it out. So this is where we're at. I got this one though. Tau is 0.5. Apparently that's how you tell it what quantile is, because we don't have enough things that are already called tau in our life. But the Stata version of the output, note that it has these words here, bootstrap standard error. So this is the part that if you reran this without setting the same seed, you'd get different numbers. And if you get different standard errors, you're getting different t's, you're getting different p's. So be aware of that. So in predicting mid-price houses, new construction doesn't matter at all. Square footage does matter, but not the quadratic part, so it looks like mostly a linear effect would be fine. What about the other percentiles? 75th and 25th. Here's what we get for 25th. This is SAS output. New construction doesn't matter. Size matters linearly only. And here's the same set of predictors predicting the 75th percentile. New construction really doesn't matter. And square footage similar. Then I get tests of each separate model, and I can also do differences across the quantiles. So you can ask for whether the slopes are stronger in one quantile versus another. In Stata, I found the same thing using SQReg to do this, and I asked for both quantiles. So it gives you all of the coefficients that would predict each of those, as well as joint hypothesis tests. Stata also anticipated that you might want the differences, and it gives you something called IQReg that allows you to test whether or not they're different across the quantiles. So, and then I found in R the same type of function where you can get two at the same time, but you have to do the differences yourself. Now this is the cool thing. I want to show you these pictures. These are from SAS, and I could not find them in Stata or R, so this is just SAS. What this is showing is, hey, what's so special about 0.25 and 0.75? Those are just arbitrary numbers, right? What about 0.24 or 0.26 or 0.27 or 0.28? Screw it, can I just have all of them? Yes. That's what these plots are showing. The x-axis is what quantile you're predicting of the data. The y-axis is what the parameter turned out to be in each of those separate quantiles. So for instance, are new houses more expensive? Well, if I start at the bottom of the distribution, here's the point estimate. You can see the error around it is quite large. So it looks like marginally yes, not as much in the middle of the distribution, and then it gets to be very wide at the end. What about the number of bedrooms? Well, this is interesting. Something happens after the 80th quantile that changes this quite a bit, although there's a lot of error around it, so you still wouldn't see it to be significant. Same thing with this one. How about number of bathrooms? looks like it's starting to matter, but mostly stays negative. Same thing here, zeros moves around. But here's the interesting one. The quadratic that was falling in and out, it depends on where you are. So at some regions of the quantile, the quadratic point estimate is actually negative, meaning that more square footage stops helping. But then it heads in the opposite direction and is significantly positive in the middle in predicting mid-range houses. So that means that more is more for the mid-range houses. And then a lot of error out here. So I thought this is super cool. So if you have outliers, if you are interested in predicting at different points of the distribution, this is what I would point you towards to do that. How's that sound? And here are words, as usual. So each of my examples has these sorts of result sections at the end of it. You may use these as templates for your homework 5. The only thing that I ask is that you use find and replace and make sure that none of my variables are in here. So if you're doing something about, the first example, for instance, ordinal was the likelihood of going to graduate school. And you're doing your report and I see somewhere in your report about going to graduate school, I'll be mad. Find and replace, okay? Promise me? Yes. Result sections are very template-y. So once you get used to writing some, then it's very easy to use find and replace, change the names of variables and things, and get a good shell of something that you can then edit into something you want. Please don't use ChatGPT to write your results sections. It's going to suck. Okay, the technology's not there yet for that. It's just not. And it always says things like, any analysis should be done carefully and with theory in mind. Like, thank you for that pro tip. I was going to do it without theory sloppily, but now that you've made that important suggestion. All right, 309. That's it. So next time then, we get to start some new stuff. I will let you know when those materials are available. We're heading into the world of multivariate analysis, repeated measures, dyadic data, mediation, path models, all that fun stuff. Woohoo! Yeah, it's super useful though, honestly. Like these are the models that tend to be used quite a bit. So, all right, let me know if you need any help with your homework. That's due on Monday. Otherwise, have a good weekend. Thanks for being here. Bye, Zoomer.